action.
All right, morning everyone. First I'd like to thank William and his local team for the invitation. I think it's great that we're having more of these sort of interaction meetings where the numerical side of the Python scientific computing world and what's being done in Sage meet up. So I'm going to give you a little bit of a view, what I think of as a view from the floating point applied mathematics side of things. That's sort of my background. I come from originally a computational particle physics background, did some work in PD algorithms, and these days I work at UC Berkeley in algorithm and tool development for neuroscience and neuroimaging data analysis. So I want this to be very informal. We're a small group, and so I'm much more interested in answering questions and discussing things with you than in following a script to the T. So please feel free to interrupt me with any and all questions at any point in time, and if we have to skip material to stay on schedule, we'll do that because I think that's a lot more valuable. So I do have a little bit of a lecture plan, but I'm more than happy to break it off and go in the direction of any questions you might have. So the context in which I want to sort of frame this discussion is one of changes that have been happening in scientific computing and sort of the kinds of problems that the numerical people are, like myself, are dealing with. Whoops, what did I do? And these are sort of not ideas that go in any particular sequence, but rather sort of the posts that surround the problem, and they're obviously interrelated, but they're a set of ideas that is really changing dramatically how people who do scientific and numerical computing have to think about what they do, the kinds of problems they're solving. One point is the rise of high-level computational systems, MATLAB, Mathematica, in your world, Magma, but the same thing has happened, and probably even before, for people who do numerical computing. MATLAB came on the scene in the 80s and really changed the world in many ways. Very importantly, now, many fields that were not quantitative and numerical, up until very, very recently, meaning the professors who are teaching their grad students and the tasks their grad students are doing are in two different universes with almost zero overlap. And that is driven by an avalanche of quantitative data. Fields like genomics, feels like these days, I saw a talk by the director for mathematical and physical sciences at the NSF, Ed Seidel, a very, very good computational experimental relativity guy, who gave a talk at Berkeley last week, and he was saying that the kind of equipment that computational biologists can get now that does in-lab genome sequencing can produce in one day roughly the data equivalent of the LHC in 1 year. Now, when I was a grad student in particle physics, several of my classmates were doing their thesis on planning the hardware for triaging, for real-time triggering of the data stream of the LHC, and at that time we thought of that as a borderline pipe dream task, right? That they could even do enough real-time triage of data in order to store and analyze what was going to be left. And now the biologists, in a machine that is apparently within the purview of the budget of a standard university lab, are pumping that kind of data in 1 day. So you can imagine the problem we're looking at. It's a mess, and in many ways it's a really nasty mess. These people are coming online to face PhD students are working on these problems with zero computational training, zero computational background. Their advisors are MDs and bench biologists and people who know very well how to draw the inside of a cell and how to recognize things on a microscope and who have never written a line of code, and for whom sophisticated computing involves writing macros in Microsoft Word, right? And they have to analyze terabytes of data per day. So this is really an interesting situation that we're facing, and the NSF is extremely worried about it and very much aware of the problem. All of this is obviously tied to the dramatic drop in cost that we've seen for computing, storage, data transfer. The phones that most of you have in your pockets right now are probably more powerful than the computers many of us were working with 10 years ago. The internet as a platform both for interaction among scientists. Sage wouldn't exist if it weren't for the internet. Linux wouldn't exist if it weren't for the internet. But also as something which enables the sharing of data and code in ways that were unimaginable just a few years ago. And all of this obviously within the context of the rise of open source software, which I think we all probably agree on, that we think about in two complementary ways. One as in terms of something whose development model is in many ways similar in terms of its acknowledgement of merit, its notion of reciprocity and credit, and its open sharing of the contributions of others to build upon, to that of the scientific literature in general, but also as a way to replace the tools, the proprietary tools that we'd rather not use. So this is kind of the context of this discussion. As I said, these topics aren't linearly in any particular sequence, just sort of the context in which I want to frame this. And for me, as somebody who does floating point, I didn't quite start writing Fortran code just because of how I ended up being taught, but this is sort of a very rough sort of, you can think of it roughly as time going towards the right, roughly, and two axes. One of the kinds of sort of numerical and computational questions that people tend to work on, and as time, the tools that are applicable for these problems, but also as time has progressed and the numerical problems have changed, also the kinds of bigger questions that people who do computing in science have started to face. So in the 50s, Fortran was more than sufficient when it was born at IBM. Fortran stood for Formula Translator, and as long as people had a way of expressing the equations they would write on paper for ODE solvers and things of that nature, they were happy. At some point, the kinds of numerical things that they needed to do started to grow. People started developing extended precision, both floating point and integers, libraries for doing more sophisticated kinds of numerical work, and eventually systems to do symbolic manipulation were developed. Maxima, the predecessor of today's Maxima, the one that Sage uses, was developed actually in the 60s by the DOE originally in the US. It was a Lisp-based system. And along that, the kinds of things that people wanted to do also started growing from purely numerical things to having to deal with data, to do text processing, to have graphical interfaces, and today to the kinds of things that we see with something like the Sage Web Notebook we've all used, the fact that many people today have to have strong ties to hardware to do their work, and the fact that today nobody uses a single programming language anymore. Sage is a great example of tying a large mass of multiple languages into one space. And the tools for this, Fortran was great in its time. Eventually Cleve Muller got fed up of his students fighting much more the problems of Fortran compiler error messages than learning numerical linear algebra, so he wrote MATLAB. In my world, Mathematica and Maple were a big deal. For you guys, I think Magma has probably, my understanding is, has played a very similar role in sort of really changing how you did a lot of your everyday work. And I guess the argument we make is that today Python is very well suited, better suited than tools like MATLAB or Magma for the kinds of problems that need to be solved today in scientific and numerical computing. So William suggested that I have a bit of a personal historical look. Unfortunately, I missed John's talk on Monday because I wasn't here, and I'm not nearly as distinguished as he is, so I'll keep it far shorter. But I will give you a very brief sort of take on what my path through numerical computing has been. So I grew up in Colombia, and when I was in high school, a friend of my dad's wasn't using one of these TI-99 4A computers that you hooked up to a TV and put a Sony tape recorder on, like the tape recorder that I had on my bedside. That's the one that you plugged in and you listened to the program. And that's where I kind of started to learn programming. Didn't really learn anything. Promptly forgot, unfortunately, didn't really do anything interesting at the time. I started as an engineering student originally in EE, and I did take one course in my life, so I guess I can't completely, no one has tried to teach me anything. They've tried, probably failed, but I did take one course, and that was in Pascal. That was all the rage. And in the late 80s, early 90s, that's what was supposed to be the next teaching language for engineering. And so, and at the end of that course, we did have to control a little wooden robot that we actually manufactured and controlled it over serial ports to do various things. And that was kind of neat. But I quickly switched to physics. And then I started doing, I had to take my first computational physics course in which I wrote a little program to plot fractals in Turbo Pascal. For those of you who may have used Turbo Pascal back in the day, you may remember what I'm talking about. I didn't have a PC at home. The PCs in the lab and at the university were known to use, so I would write on paper. I would write all the code on paper, think a lot about it, and debug on paper, and work on my mom's computer in her office on weekends when it was available, and go and type it in. Probably many of you have done similar things. One interesting aspect of working like that is you actually think a lot about your code. Since you don't have the screen in front of you, you tend to really think a lot. I remember for a while I had a bug and things weren't working at all, and the images that came out on the screen had nothing to do with the equations I was typing in. And it was middle of the week, I didn't have access to the computer for days on end. And one day I was at home doing homework on a different problem, and all of a sudden it hit me, oh my god, the matrix is transposed. The affine, I had transposed the affine that you have to apply for kind of iterated function system fractals. And I literally called my only neighbor, the only guy in the neighborhood who I knew, his sister was in college and they had a computer at home where I could borrow it for at least a half hour to see if I was right. And I raced to his house and sat down and transposed two indices. It worked, and I ran back home screaming. But you think a lot about that. And I was in the middle of doing something completely different. And yet, all of a sudden, it just stopped in my head. It's transposed. And I had to run in. And I don't know if we've lost a little bit of that way of thinking about computational problems because we are so close to the code and we have such a rapid feedback loop. I mean, I'm the guy who loves interactive environments. I love IPython. Obviously, I want rapid feedback loops. But sometimes I wonder if I think as hard about my code these days as I used to when I didn't have that immediate feedback loop. Anyway, I didn't know what free software was. I didn't know what the internet was. I have a little anecdote. I actually unplugged Columbia at one point in time. I don't think many people can actually claim to have unplugged their country. I did. When I finished the undergrad, Columbia was just getting plugged into the internet. There was a consortium of a handful of universities that had access to the internet, and the government was trying to expand it. And one of my physics professors told me, I was in charge of that, and he said, I want you to work with me on this thing for a few months. The president is inaugurating this thing in a few months. It's a big deal. We need it up and running. I said, I don't know what the internet is. He said, here's a book. One of those Well books from the 80s. And he said, here's a book, read about it, come work with me in Bogota, we'll sort out your finals with the university and have them delayed for 3 months. I said, okay. So I go and I said, I have no idea what the internet is, I don't know what a network is. I had a home PC, right, with floppies. And so I went to Bogota and we started working like maniacs, and the country had a satellite link, a 128K satellite link whose downlink was in the outskirts of the capital, and then it was sent via radio modem to the place where we were, which was sort of the equivalent of the Library of Congress, Columbia scale, near the airport. It was a big library, and that's where the databases were, and a big VAX machine was, and it was going to be inaugurated there. And so that radio link landed on an antenna in the roof, and there was a radio modem there that would catch it and then distribute it to the other institutions. But we also had contractors installing PCs in the library for databases and whatnot and surfing the internet. And one day a contractor says, I need a coax cable. Do you have one? I said, I've seen a coax cable. There's a coax cable. Nobody's using this thing. I've never seen anyone working with this thing. I'll get the coax cable, go back to my laptop, to my PC to work. And then about 2 or 3 hours later that afternoon, a phone rings and somebody says, hey, so I'm calling here from the satellite downlink station a few hours from Bogota. We're getting reports from all over the country from the institutions that the network is completely down, and we've kind of bracketed it to you guys. Do you have any sense of what could be going on? Have you guys had a power failure? And I said, you know, I think I know what's going on. Why don't you just give me a few minutes and call me back in a few minutes? I think I may have an idea. Go back, plug it back in, go to my computer and print a big thing. Never, ever, ever unplug this thing. Tape it to the thing and go and tell my boss, I unplugged the internet today. So I was more successful than Gaddafi and all of the other ones who tried to shut their entire countries down. I actually unplugged the country. But not knowing what the internet was meant that I had no sense of collaborative work. This kind of computing was done sort of on your own. when I did my undergraduate thesis, I worked on the electrostatic three-body problem, numerical simulations of the electrostatic three-body problem. If you don't restrict the masses and charges, it turns out that there's a number of numerical instabilities, and so you want to transform things to a different coordinate system. And so I started sort of getting involved with working in mixed languages. I used Maple to do a lot of the analytical work. Is relatively straightforward, but tedious and easy to make a sign mistake. The equations are big. You transform the coordinates, and you get a large system of ODEs where the algebra is just easy to flip a sign somewhere. So I would generate the equations in Maple, make them spit out the C form, and then paste that. So it wasn't automatic in real integration, but it was sort of the idea of first integrating languages, and second, it was the first time that I started thinking of code, generating code that is adapted to a problem. And this is an idea that I want to get back to at a few points in this discussion, because I think it's a topic that's becoming increasingly important for all of us. The notion that the compiler and the code generation should be part of the problem solving, not something that happens at the stage when the scientist is thinking. And that worked reasonably well. Then when I finished undergrad, before I came to the US for grad school, I had to teach computational physics course for undergrads. We were a poor institution. We had an old VAX machine, and somebody had one 486 PC, and a student who was very enterprising had installed Linux on it, and he said, well, I can help you hook up the VAX to the Linux PC, and we can teach. You can teach with that, because we have very few tools, and at least you can get GCC and GNU plot, and there's an editor, and the tools are free, so you can teach the whole class there. It was a complete disaster. I promised to myself never, ever, ever again to teach a class with tools like such low-level tools when you're trying to teach people about numerical algorithms and their importance in specific physics problems, because I had students who basically spent the entire semester extremely frustrated with compiler errors, sec faults, and pointer problems, and never understood anything about the numerical algorithms or the physics, except for one student, the one student who probably would have done it on his own anyway. And so it really taught me that for these kinds of contexts, you need tools where there's a much narrower gap between the ideas you're trying to express and what the tools can do, because otherwise, if that gap is too big, most people will fall through that gap, and very few people will bridge it effectively. And they weren't stupid, and they were trying hard, but there were just too many pitfalls imposed by basically the same observation that Cleve Muller had to run into when he wrote MATLAB. I didn't go and write MATLAB. I simply said, I'll never do this again until the tools are better. Much more lazy. In grad school, I was busy, the way grad students are, trying to get homework done, trying to keep my nose above the water. I used Mathematica and IDL for most of my work. Mathematica for symbolics, IDL, which is a tool very similar to MATLAB. If you've never heard of it, it's just more popular in physics, and it came from CU Boulder, so it was a naturally widely used there. Not very nice tool to use, but a horrible programming language, but it got the job done. Similar sort of plotting, interactive work, numerical libraries. My thesis was on QCD, and there, at that point, I started sort of seeing the power of collaborative work, because the large computations that I was doing were based on a C code, which is collaboratively produced. It's open source. It's a code widely used. It's one of the codes that is used to calibrate the large supercomputing machines that's so CPU intensive, so that whenever you see a national lab putting out a new big supercomputer, one of the big runs they do to calibrate and benchmark and stress test the machine is a run of the Milk code. But there, I had a hodgepodge of custom C code in Mathematica and IDL and bash scripts, but the bash scripts made set calls and awk and Perl, and they piped it to GNU. It was a mess of 17 different languages that I was dealing with. At one point, a postdoc told me, you should use Perl for a lot of that, it'll make your life easier, and I started learning Perl, and it was true, it did make some things easier of sort of managing, because I was just drowning in mental context switching between languages. And I remember one day looking at my desk and seeing, I have more programming language books in here, one for each step of what I'm trying to do, that I can really keep in my head at the same time. And towards the tail end of my PhD, whether because I finally had to get something done like write a thesis, I found a much better excuse, which was my office mate told me about this Python thing. He said it was cooler than Perl. And within about 24 hours of learning, at that point I was a decent Perl programmer, not great, but I knew what I was doing. I'd written some open source software in Perl that had some use, something to get from licks to HTML, and it was reasonably widely used. And that also produced PDF out of licks when licks wasn't very good at it. And he said, this Python thing is very nice, why don't you play with it? And within about 24 hours of reading the tutorial, I realized I could do things in Python. I immediately saw how to do, and I tried, and they worked, that I had no idea how to even begin doing in Perl, despite the fact that I was a pretty decent Perl programmer and had a few books. And then I realized, forget it, this is the tool to use, and this thing will take care of a lot of what's in this slide right there. Not all of it, but a good chunk of that I can compress out and replace with a single tool so I can reuse. Yes?
Do you remember any examples of that? Like things that were easy to do in Python that were hard for you in Perl?
I remember things especially with object orientation. Just to give you an idea, there's a whole book called Object-Oriented Programming in Perl. And just a few days ago, I was just browsing the internet and I saw a big debate on one of the Perl development mailing lists about which object-oriented tutorial and framework Perl should promote. So the fact that this is like, we're at 2011 and this is a core discussion in the Perl community, how to do object-oriented things. And whereas in Python, I was like, oh, okay, and I can do that, and I can add this behavior to an object, and I can modify the built-in behavior of the objects and override. So these things that in Perl were like, oh, you need to be a guru before you go there, and the book is yay thick. In Python, we're like, okay, you read the tutorial, you type it, and it just works. Yeah. The gap was just ridiculous. And literally within 24 hours, I knew I would never write a single line of Perl again in my life, and I haven't. So then in my postdoc, I got into numerical algorithms for PDEs, and this was a very interesting project because what we were trying to do was develop algorithms to efficiently solve PDEs in an interval formulation, effectively to efficiently apply Green's functions in multiple dimensions. And the problem of this approach, if you formulate it naively, it has excellent numerical stability properties. It's sort of the right way to phrase a PDE in many cases. But unfortunately, naive applications of the idea lead to very large, very dense matrices with very few avenues for efficient application. So a large swath of the PDE world has gone to the approach of inverting ill-conditioned differential formulations where you spend a lot of time on preconditioners and multi-grid methods and that kind of thing. What we did is sort of something along the lines of, for those of you familiar with the fast multiple method, of basically finding decompositions of the operator where you extract sparsity out of an operator that appears dense. I don't have time to go into all the details, but basically it's an algorithm with, at the end of the day, what you're doing is a big matrix vector multiply. You can think of it as a large multidimensional matrix vector multiply, but a very, very ugly and complicated matrix vector multiply. And there's enough bookkeeping and there's enough data structures involved that doing this in a language like Fortran would have been an absolute nightmare. To give you guys an idea, the fast multiple method, considered one of the 10 algorithms of the 20th century by the ACM, is something that took the team that invented it a number of years to go from the 2D adaptive implementation to the 3D adaptive implementation. And the 3D adaptive implementation was never actually published because my understanding is it was developed mostly for a big company that flies planes nearby, and for the defense contractors behind those guys, because it was a major piece of intellectual effort by some of the arguably the best numerical computing guys on the planet for a number of years. With this project, we were able to get the prototype working in one dimension, and we literally, once I got the data structures right and was able to understand how to generate and abstract out the problem, I got the 3D code working. And when I went to talk to my boss, and he said, you need to benchmark it against the FMM papers, we went looking, and there were no public benchmarks of the 3D version. So I had to backtrack down to 2D, because the FMM work had only been published in 2D, and the 3D code, the 2D code took a long time, and the 3D code never came out, and there were no published benchmarks. And this was an interesting example of how, in Python, once you had the combination of tools to represent the abstract data structures, the ability to weave together Fortran tools that my boss had written, handwritten C code for some of the performance-critical linear algebra pieces, and to auto-generate, a big part of it was that I could see what some of the key methods were and auto-generate C++ on the fly, so that once you defined the geometry and the parameters of the operator, you would take, and basically the code would generate C++, take templates, basically string templates, fill them in with all the relevant data, expand the loops to the necessary dimensionality, and then just called something called inline that was part of SciPy, recently replaced by Cython, thanks to Robert and a bunch of conversations we had about it. Now Cython does this. You could then compile compile that thing and replace the method for multiplication or addition in that object by a compiled version that is specific to that problem. So object instantiation got a little bit longer because you had to wait a little bit for the object to be compiled, for the code to be generated and the object to be compiled. But then you had this thing that applied very, very efficiently and was tailored to the dimensionality and values of your problem. So again, coming back to sort of this idea of thinking of code as something that happens during problem solution, not something that only happens before problem solution. And with that, the project worked very, very well. So that's sort of, yes, questions? Yes, yeah. Please.
Sort of in a similar vein, there are some problems in nonlinear, computational nonlinear PDEs, in particular integrable systems where to compute solutions, you need sort of a healthy dose of both symbolic computation as well as numerical computation. And you had a bullet point on your previous slide about how it goes beyond pure numerics.
Yes.
And I was wondering if what your thoughts were on do you see a trend where software is sort of trying to bridge that gap, include both numerical and analytical computation sort of working together, or do you feel that's still sort of a separate tool, separate problem?
No. There's a huge trend in that direction. I'll come back to that. I'm happy to talk to you about it afterwards further if you want more detail. There's a huge trend in that direction. The fast multiple method that I talked about was developed by Vladimir Rocklin at Yale and Leslie Greengard, the director of the Quran Institute at NYU. His current postdoc, one of his current postdocs, of Greengard's postdocs, is Andreas Glockner. He's the author of PyCUDA and PyOpenCL, the Python bindings for all the GPU machinery. He's working on discontinuous Galerkin solvers that basically use exactly that idea of a symbolic piece of machinery that takes the operators, generates the relevant code, and emits GPU code for the application of the operators. And I was in Reno 2 weeks ago at the Science CSE meeting, and there were large swaths of Python-related talks from the PDE people, a lot of it going exactly in the direction you're talking about. So if anything, that trend is huge. People recognize that, and people realize that a tool like Python that is very good at high-level representation that may not be the most efficient for computation, but that are the right way to describe the problem, coupled with the fact that you have very flexible ways of manipulating those objects, transforming them. It's easy to write symbolic machinery. There's SymPy. Some people are using SymPy for this, or their own libraries. And then at some point take that, and you have very good string processing facilities, because at some point you have to compute strings, because typically somewhere you have to feed it to a compiler. But having rich, flexible, high-quality string manipulation machinery and templating machinery makes that step feasible. And the fact that there's very good dynamic loading facilities, the ability to call a subprocess, maybe call a compiler, pick up a piece of code, load it at runtime. All those things are a pain in the ass to do in a language like C, right? And they're very natural to do in Python. You can compile something, you get the name of the module, you load it. The module may be something hidden in cache whose name is some MD5 hash of the source code. Who cares? And the fact that that chain of steps, none of those steps is particularly difficult in Python, makes that idea of closing the loop between the symbolics, basically saying the scientist working on the problem reaches one point of the symbolic description, but from that point the tool picks up that symbolic description and continues doing work yet on the symbolic description before emitting the relevant numerical code for it. That is absolutely the way I think things are going, and that's why I've been trying to make that point at a few places, because I think it's actually an increasingly important idea. You had a question.
Yeah, could you just take 20 seconds and tell us a little bit more about what Cyfun is?
About?
Cyfun.
Cyfun? Mm-hmm. Oh, I thought everyone here had seen the talk on Tuesday. I wasn't here on Tuesday, okay. And so I actually deliberately skipped explaining what Cyfun was because I thought that everyone in the audience knew what it was, but I'll be more than happy to talk about it. So Cyfun is a project that was started by William Stein and Robert Bradshaw, picking up an existing project called Pyrex that was there before.
Cyfun. Okay. Right.
Cyfun.
Okay. Sorry. What does he think? I had a different spelling in my head. Never mind.
Oh, okay. Sorry.
I was thinking Cyfun like sci-fi is Cyfun, but...
Oh no, Cyfun.
Yeah.
That's what. And what I meant was that Cyfun recently picked up inline. Yeah, sorry if my pronunciation is.
No, never mind.
So
that's a good name for a project, though.
I was thinking sci-fi functions or something. Yeah.
SCI.
Oh, Cyfun.
Yeah,
SCIFUN. Got it. Okay. No, and Cython, the reason I was mentioning it there is because it did pick up recently exactly the inline machinery. At one of the MSRI meetings we had last year in Berkeley, where John and William, or Robert was there as well, and we started talking about Weave Inline, which is this ability to write C++ code that looks at your local scope and is compiled on the fly. So you can basically put a string in a little loop of C++ to operate on your local scope. That was one of the very useful parts of SciPy Weave, but that project was semi-abandoned. No one was really maintaining it. SciPy has just been ported to Python 3. The one part of SciPy that didn't make it to Python 3 was Weave. It's old, unmaintained code, but very useful. And, excuse me, I had some discussions with Robert about it, and then back with Kurt Miller at SciPy 2010 in Austin, and they implemented all of that. So basically, Cython is now more or less a complete, it's almost a complete replacement for all the SciPy and the NumPy F2Py machinery. So we're finally having in Cython, a unified tool for Fortran, inlining, and all the other things you already know Cython does well with one unified interface, which is what makes Cython such an awesome project in every way possible. So now a little bit about what I think of as the core tools, and I'm going to go quickly through these. But I'm happy to go into details if anyone has questions. NumPy is sort of the foundation of everything we do in numerical computing. It's a flexible, very nice multidimensional array object. And the idea of an array is something that contains homogeneous elements, but actually the word homogeneous here can be interpreted fairly flexibly, because yes, you can have an n by m array of floats or ints or whatever, but because you can hold pointers in it, it actually can store arbitrary Python objects. So it's much less restrictive than you would think. So it has nice syntax for high-level operations. A plus B does what you expect it to do, and it's evaluated in a fast C loop. It comes with a math library that operates on arrays, so the version of cosine in NumPy knows what to do with a whole array, and it does it reasonably efficiently. And it ships with very basic scientific functionality. Basic linear algebra, basic FFTs, and basic random number generation. It's kind of a minimal toolkit for numerical work, and very importantly, the data structure. Because the data structure...
And statistics.
NumPy has very basic statistics. SciPy stats has more. Does NumPy have a whole lot of stats? I thought it had...
Certainly in the NumPy manual.
Oh, okay.
I remember flipping through all the distributions listed in there and stuff. Maybe the code got moved though. But
oh, you know what? It's possible. Yeah, it's possible that NumPy random, because the random number the random number generator module may have a fair amount of distribution. Yeah. That's right. Yeah,
but also even computing just things like standard deviations on matrices, like
yes.
I mean, there's a lot of covariances. There's a lot of higher dimensional statistics stuff that's optimally implemented.
That's absolutely true. They have methods like cov and std and var that do the right thing, and they do it along an axis and along dimensions. Because
cool.
The idea is that the NumPy array should be a very easy and convenient way of expressing multidimensional data. So it's not a matrix library. It's an array library. So you can think of it, if you will, as a tensor library without, and so probably the closest thing that an array matches to is probably a tensor much more than a matrix. And so, as I said, they're homogeneous. What they contained is represented in an object called the D type, the data type. And these D types can be user-defined. So not only can they be opaque pointers to arbitrary Python objects, you can actually define the data type of an array to be, for example, my array contains actually an int and a float and a 4-byte string. The only restriction is that the entity that goes into one of the little boxes, so the ND array is basically a header with a description of the data type and a big swath of linear memory with information on how to walk that memory dimensionally. So basically you have a striding information, where do you start a new dimension as you walk this bank of memory, right? And what's in one of those boxes, right? But what's in there, as long as the boxes are the same size, you can say, I have 2 floats, I have an int, I have a string, whatever, right? And so it's a very, very flexible data structure. And you can name those fields, so you almost have like a little mini spreadsheet in an array. And one thing we're working on now is on adding, right now it's still on GitHub on my side because we haven't really pushed it upstream, but the plan is to hopefully work on this to push it upstream, is to have similar ways of describing not just what's on the inside but what the geometry, basically what the axes contain, and labeling the axes and whatnot. And this is the kind of functionality that people miss from R. That's what the R data frame provides. So we're working on effectively extending the NumPy array in that direction as well, so that you can have both rich internal structure in the containment cells and a proper description of the dimensions, and so that you can write algorithms, for example, that loop over the time dimension. So that if halfway through your project you change your code and you add a new dimension to your study and you need an extra loop, you don't have to go hunting down where is the third comma in all my loops and moving it and adding one more comma, because you write your code in terms of loop over the x and then y and then t. And if you add z in the middle, then nothing has to change, because the code knows what t is. It's just that, okay, well now t is the third instead of the second. Who cares? So that we're trying to get that pushed into NumPy itself, and hopefully it'll happen soon. SciPy sits on top of NumPy. It's basically a large collection, if you will. It's netlib in Python. So it started as netlib in Python. Netlib is a website that contains a lot of the large, well-used, battle-tested Fortran codes that are available from the numerical community, and many of these have been wrapped in Python. And in addition, a lot of new code has been written. And so SciPy is a fairly rich collection of tools for numerical computing. I list there some of them. Eventually, on top of SciPy, something called Scikits was developed. The idea was, in order not to completely bog down the development of a very large monolithic system, let's allow people to develop their own toolkits on top of the NumPy and SciPy machinery with a uniform namespace, uniform conventions, a uniform website to download them, but so that people can develop kind of domain-specific toolkits. And it's possible that some of these things will make their way into SciPy proper over time, but you want to give projects a chance to test themselves, to prove themselves, maybe to compete. If two people have a different idea about a problem, see what works best. Very similar to how the Python standard library works, where they sort of allow projects to bake out in the wild for some time before they say, okay, we're going to merge you into the standard library. Yes, Willie?
Do these typically have like their own namespace, or do they often install into SciPy? So when you import, I don't know, ODS or optimization, is it import optimization or import SciPy.optimization? I'm just curious how they're laid out. So do they have to be somewhat rewritten?
So these import into SciPy optimization.
But I'm curious about the Scikits.
Import into Scikits optimizations, literally. There's a Scikits namespace. Okay. So Scikits is what's called a namespace package, which means that's a package. That's PEP 382. It hasn't been merged into Python proper, but Setup Tools provides an implementation for this, so that already exists. And this will be merged into, the plan is to do it for Python 3.3 in the core itself, but it already works. So there's a common Scikits namespace, which is an empty placeholder. And then you can install pieces of Scikits in different places. So you could have a system version of scikits.eartho, but you could install in your home directory scikits.optimization, for example. Now, if one of these is going to make its way into SciPy eventually, there will be a small amount of rewriting, but because the hierarchical structure is very similar, it'll be, I don't know, a day or two's worth of work. So which in the grand scheme of things is not a big deal.
Yeah, we have a similar setup with psage, where you have a separate namespace for a bunch of experimental code, and then Sage for the more stable code. But I'm not using this. But I mean, psage is just one big package as well. It's not broken up into a lot of smaller packages.
Okay.
And that's pretty cool that you can have one namespace and a bunch of smaller packages that install separately.
Google the term namespace packages. The PEP is 382, I think, or 384.
Cool. Nice.
But the implementation has existed via Setup Tools for a number of years. It's just that finally they're trying to bake it into the core machinery. Rather than being supported by Setup Tools kludges, it's being they're working on merging it into Python itself, which will be much better.
Yeah, that's really
but it already exists. The one drawback it has is that on NFS file systems, it tends to cause very large searches. So sometimes if you have namespace packages on NFS file systems, you may feel the performance hit. So it's the one thing that you want to think about. Yes?
How successful do you find this model? Do you see a lot of projects being actively developed out here in
yes.
and then being merged in? Or?
Well, not merged in, and I think that's good. That for a while they live on their own and they're healthy and they have their own mailing list and I think that's actually good. It allows some decoupling for the projects to evolve at their own pace. But some of them I don't know. Some of them I have no idea about. Some of them I follow relatively closely. The machine learning one and the image one, those two I happen to know, and they're super active, very well developed. So some of them may be dead for all I know, but I know that at least some of them are being successfully and actively developed. As always with open source software, caveat emptor, go and have a quick look before you start using it. Get a feel for the mailing list. Is someone really working on this or not? Okay, so quickly, I'm gonna, wow, we have We'll go quickly. IPython, interactive environment, you've used it at the command line.
Don't worry too much about time, because
okay.
I mean, it's not like we have a ton of talks and stuff.
But yeah, okay. But at the same time, I won't run over it for too long. So it is, what IPython is basically trying, when I switched to Python, I realized the one thing I'm missing is a good interactive environment. We're all used to whatever Perry, Gap, Magma, Mathematica, MATLAB. Python has an interactive shell, but it's very primitive, so I tried to do better, or also I tried to find an excuse to not actually write my dissertation. But anyway, what came out of it was a useful tool. It's the shell that you guys have used if you use Sage at the command line. That's basically a modified IPython. It's something you can embed. It's something that integrates with GUI toolkits. It's something that you can put in other environments. But it's also something that has very nice high-level Perl computing interfaces, and we'll talk briefly about that. So the basic system was really born out of the need of having something like a MATLAB shell or an IDL shell where you can type, where you can have GUI windows that are separate and that don't block the window where you're running, the ability to run a script. My workflow has typically been Emacs for the scripts, IPython for the code. There's a command called run in IPython that executes the script and loads all the variables into your working namespace for further kind of interactive exploration. Once you know what you want to do, you go back to Emacs, keep editing. And that's kind of a very typical workflow in the kinds of things that we do. And a ton of floating windows, matplotlib windows, you can pan and zoom around them and whatnot. And we work very hard to integrate with all the toolkits so that if the floating windows are in Qt or in WX or GTK or any of those, they still work and they pan and they don't block the shell. That's a pain in the neck to do, but it reasonably works. It has been fairly successful both in the scientific scientific world. Sage is one of its users, but there are many others. I guess this probably should have been put on the other column, but recently Visual Studio, Microsoft just came out with tools for Python. Interestingly enough, where is it? So Microsoft has now, your neighbors up here, they have Python tools for Visual Studio, and one of that just came out, and one of those is a set of IPython integration. So you can now basically load IPython inside Microsoft Visual Studio if you're a Windows developer and are interested in having interactive support. You can do the basic one, or you can do somewhere in their pages. They have the IPython, IPython Quick Start Guide, and they also added the cluster support, the Perl computing, even though what they're using is the older version that we don't like as much as the new one that is much nicer. It's also fairly widely used by non-scientific projects as well, kind of web frameworks and other things that want an interactive environment. But what I want to talk about now is the idea that if you look at an interactive environment, in its most basic form, you'll often see the acronym, it's a REPL. It's a read about print loop. Which basically means take user input, execute it, and provide output. And if you add support for data transfer, it turns out that interactive work and parallel computing actually look very, very similar, because they're basically both things that are trying to manage a namespace. They're basically, you're trying to give instructions to have something happen in a namespace and have something change in that namespace. If you read NPI code, you can think of it basically as code that it's telling, over there in that namespace, I want this to happen, or I want you to get this piece of information, or I want that piece of information which you have to be sent back to me. And so, first of all, these steps can happen in multiple processes. This is not news to you guys. You use the Sage notebook all the time. In the Sage notebook, you read in a web browser, it evaluates in a kernel process over there, and you get back your information into the web browser. So this is not news to you guys. And so what we're trying to do with IPython these days is to, we spent a fair amount of time carefully sort of looking at what this entailed and what the kind of workflows we could achieve if we took some time to sort of look at the patterns that are here and what kinds of things can you do with it. And we realized if you have some place where code is being executed and you define messages to go back and forth between the thing that is controlling it, but also you specify what information that kernel may put out into other channels that are publicly broadcasted channels, so that not only are you sending commands and data back and forth, but you also have a way of the kernel informing others, then there's a number of things that you can do that are interesting. But that meant that we thought very carefully about what information had to go back and forth, and we defined a messaging protocol between clients and a kernel. We specified it completely. There's a document in our docs that specifies what parts of the communication are meant or should be direct communication, like execute code or introspect objects, like the things you do with a tab key, the things you do when you do question mark, information about what has been done before, what kinds of things should be broadcast, and once you start thinking about it, you realize that you basically want to separate two. Yes, Willie?
Can I ask, so you guys switched from using twisted for many years to 0MQ.
Yes.
And this is, of course, closely related to defining your protocol.
Yes.
Did you kind of redefine everything when you switched to 0MQ? Or, I mean, I'm just curious, like
yeah,
how this picture, did it dramatically change when you switched to 0MQ, which seems to have been a very, very good switch?
Yes.
Looking at your...
We only really use twisted for Perl.
Yes, we only.
Oh, I see. What did you use before?
Right.
I mean, you used twisted before.
We didn't have, so it wasn't a two-process.
Ah, you didn't even have this until 0MQ.
So this is all new, and we use twisted for the parallel computing stuff.
Mm.
And
So you defined all this partly because you were switching to 0MQ and had the option to really
Exactly.
do
we
all kinds of cool
had
stuff
the
you
option
couldn't
of
do.
Doing a two-process,
Nice.
two-process single session
Yeah.
with the ability to gracefully handle site faults and things like that.
Yep. Cool. Cool.
Exactly.
Yeah. 0MQ is really cool.
So we went through kind of the exercise of deciding what this should be. We scoped it out. And yes, this was driven to a large extent by 0MQ, and I'll get back to this. Because what happened was we found out a year ago, I was just about to the day a year ago, I was in Columbia teaching a computational physics course. Now in Python at the same institution where I said never again. I finally came back with the right tools to teach it, and it went much better. And I was there reading Linux Weekly News, and I read a little snippet about, oh, this new library called 0MQ. And I read up on it, and it sounded like a very interesting tool that might solve the kinds of problems we had with Twisted. And we had looked at something called AMQP a while ago. Brian Min and I had looked at it. It was a library from the financial world. It had some interesting ideas, but it was very big and very complicated. And then 0MQ was something that was written by the AMQP team. The team that was hired to implement OpenAMQP wrote this thing, basically after learning the lessons of AMQP and trying to distill it down to the core ideas. It looked very cool. I Skyped with Brian from the university and I said, look, I'm teaching here in Columbia. I have a big class. I'm teaching, lecturing every day. Can you have a look at this? It seems really interesting. And 3 days later, he emails me a GitHub link. And he said, look, I've got the bindings written in 3 days in Python. Nice. It's a tight C++ library in pure C++. It doesn't hold the GIL. The messaging happens in C++. Your code, the moment your code has made a send operation, your code can go into Python or Fortran or C and block the hell out of everything, and the messaging and the networking will continue to happen nicely.
All in one process.
Excuse me?
All in one process.
All in one process. It's a native C++ thread that doesn't touch the GIL, that doesn't touch any Python data structures. It's absolutely beautiful. The abstractions are at the messaging level. So when I came back from Columbia, my wife was still in Columbia and had a weekend off. And I called Brian and I said, why don't I drive down to your place for a weekend and we haul ourselves up for 2 days and see what we can do with this thing. So I went down. I'd never used 0MQ. I just read about it. And he said, okay, how do I learn? I said, how do I learn how to use this thing? Okay, build it and install it. 10 minutes. It's quick. Said, okay, open an IPython shell and import it. He opened one on his laptop. We were at his house. And he said, open a socket, okay? Here's a message. Grab the message. Send me a message back. Literally in about 20 minutes of experimenting with the library at the command line, I had understood what the messaging patterns were. And then we tried to write the core idea of what I just said here. Can we write something like this? And in 24 hours, we had a working prototype. No IPython in the picture. It was a tiny example, 400 or 500 lines of code. He wrote, I don't remember, one of us wrote the kernel and the other one wrote the front end. We literally wrote iteratively, debugging, by keeping one of them open in one laptop, and we would debug the other one we started. And then when that was fixed, we would leave that one running and go back to the other one and debug that. So it was literally live debugging of the two processes across the network from the two laptops in his house. And the day after, when I drove back to the Bay Area, we realized this is the way to do this. I mean, the fact that we were from zero to fully working prototype with remote tab completion, with all the abstractions, right? Now we just have to take a step back, think about the messaging, define the protocol. So what I just said that happened actually happened after the fact. What we first did was get together and prototype it. And the prototyping effort went so amazingly well and was so different from everything we had experienced with Twisted that we said, this is kind of one of those moments like the Python Perl moment where you say, okay, this is the way to do things. And so the beauty of ZeroMQ is that the sockets it creates encapsulate messaging patterns. You're not pushing bytes. You're not pumping the socket for bytes. You say, I need a socket that encapsulates back and forth two-way communication. That's a type of socket. And then on that socket you send and receive and you're done. You do send or receive and you're done. Or you say, I have a guy who wants to broadcast information and I have guys who want to listen to the information that is being broadcast. Then you do that. You create a pub socket and that socket broadcasts. And then you create clients that have subsockets that bind to that socket, and then they listen, and they can actually filter the streams of information coming from it. So the library, the abstractions of the library, it seems fairly low level, but it's in my mind at the right level, because it is low level. It's not big web frameworks. It's sockets, but they're sockets that represent flows of information, not transfers of bytes, and that actually makes a big difference. So what we did was, once we understood that, then with the messaging protocol, we implemented the interactive part of IPython based on this, where now we have a kernel. The kernel has several sockets. It has a socket that is a multiplexed reply socket, where it can take requests from clients, but it can take requests from more than one at the same time, because ZeroMQ makes that absolutely trivial. It's just a different type of socket, so that more than one client can simultaneously talk to the kernel. It has a socket called pub, where it broadcasts information that they can all subscribe to. And it actually can have a request socket, because if the kernel code needs input from its side, say the kernel does raw input, then who's going to give it input? You basically can teleport to the keyboard by having one of the clients have a socket which basically is taking input where there is a real keyboard and feeding it back there. So basically we have the architecture for breaking up what is normally a single process idea of the read-eval loop into two processes, with the possibility for collaboration, with the ability for all of these connections to be severed at any point in time and reappear. For clients implemented in different languages, the client, it doesn't matter what the language of the client is. It can be JavaScript, it could be Java, it could be whatever you want it to be. This is a messaging protocol. We're sending JSON over ZeroMQ. That's all we're doing. It's JSON over ZeroMQ, and the messaging spec is completely defined in our website.
Much different world than Twisted.
Oh my God.
Yeah.
Oh my God. And by the way, the Pythons, we control them, because the Pythons were, the Python bindings for ZeroMQ were written by Brian and now also maintained by Min. So we have end-to-end control. B, Python-3, and we have Python 3 bindings. Yep. Twisted 3.
It's actually simpler than that.
What's that? Oh really? You don't even need that?
You don't need that. You run Python with no options once, and it just runs on every Python. No 2 to 3, no Python-3 run.
Wow, I thought you needed that -3 switch. Well, even better.
It just generates code that works with either one, using hash defines and stuff. Yeah.
Whereas Twisted on Python 3, it's like, yeah, maybe in 10 years.
Yeah.
Yes, question.
JavaScript, ZeroMQ.
I'm sorry?
Can we connect to the ZeroMQ?
C++.
Yeah, but can we connect to a ZeroMQ socket using Java? You mentioned JavaScript.
So right now,
you would need something running a bridge from. So you would need a server of some kind that bridges like WebSockets to ZeroMQ sockets.
Okay.
and we have some prototype code to establish that bridge, basically, to broadcast over, basically to convert the ZeroMQ transfer to HTTP so that it's JSON over HTTP, and just with one layer that does the translation into
Brian
ZeroMQ.
is working right now on possibly putting a WebSockets bridge in Tornado as part of PyZeroMQ.
So late last summer, Enthought sponsored, and I'll try to give a very brief demo of this later at the end, sponsored the development of a Qt console. This thing, what you're seeing there is just a screenshot. It's something that feels like a terminal. It's deliberately like a terminal. It's text-oriented, no menus. You type and it feels like a terminal, but it's multi-line. You can run plots and the plots show up in line. It has syntax highlighting. You can do multi-line editing. So it's not a notebook. It's not meant to be a notebook, but it's basically a terminal where you can not be annoyed that you're typing in a read-line limited environment. Yes.
Would it be trivial for you to demo that, or would it be hard?
No, it's trivial. I was going to do it at the end. I'll do it right now. It's
because
great.
I saw Mike Hansen and I were using it at the last Sage Days, and it's I don't know, it's much better than what you expect from the picture.
Thank you, Will.
It's really amazing. Yeah.
Is that a compliment?
It's surprisingly powerful.
I assume it's cross-platform.
Test it on Mac, Windows, and Linux. I don't know if it runs on HPUX or AIX or some bizarro thing. And test it against both the PyQt bindings and PySide. So you can define a Qt API environment variable and choose whether it runs. We actually, Evan Patterson, the Enfa developer who did that part of the Qt part of the work, did actually find bugs that made it into PySide 1.0 that were segfaulting that were discovered by this project, and they managed to get in before PySide 1.0 was out. If you want to ask, you type GUI ref, and it gives you a little. So it gives you a little bit of information about how to use it. This is a rich text widget. This is actually REST converted to HTML and shown properly. You can go back between this and this. You can close it. I'm not using the keyboard. You can do plot.
So it's much more impressive than you might think.
Excuse me?
You do a question
it's
mark,
much more impressive.
Yeah. Wait,
so you do question mark, and you get the browser here, and you can go back and keep typing. If you do double question mark, the usual thing happens. In this case, plot is very short. It is, yes, it is properly syntax highlighted. It does the usual thing. If it fits in the screen, it shows it inline. If it doesn't, it opens the little pager. The little pager can be vertically split or horizontally split. If you do plot rand 100, you get a plot, and these figures can be floating or they can be inline. You can move them, you can pan them. You can say, oh, I want that figure here.
Could the Sage command use this?
Yeah.
I'm sorry?
That's dynamically coming up with the help. Is that what we're seeing? Every time you type it, open parentheses?
Yes, yes. So it's using the object. Remember how I said we have an object, we defined a protocol for object introspection. It was important to have in the protocol the notion of an object information query that was separate from the code execution because you haven't hit enter yet. So you want to detect that an object introspection event is happening and send that request to the kernel without having to send a code execution request. So that is part of the messaging protocol. If you grab this now, one thing that is sort of neat is that in here it tells you what sockets have been opened. So I can open another one with the same sockets. So this is another session, and now you see I get that prompt. And if I do up arrow,
or set variables, it's all the same Python session.
Yep. I can even capture the same figure. And these could be two different people in two different places. So you've popped up the window, you've zoomed in interactively, and you're Skyping with someone, and he can say, display get figures, and grab the figures, and one of or all figures, you can grab one figure, you can grab them all, and get them into your local thing. This guy, you can close it. And if you close it, it'll say, what do you want to close? Do you want to kill the whole thing or just this console? No, I just want to close this console. X is equal to 1. Now you see that the prompt got rewritten because another input had happened in the other one. So the prompt got rewritten in order to ensure that this is the right thing. And if you reopen another one and you look at what X is here, it's one. They're operating on the same namespace. They can do it collaboratively. You can close them all and open new ones. So it really is vastly, vastly superior to anything we had before. It has the notion you can do proper multi-line editing. Obviously, many of us really like the matplotlib gallery because it's a very useful way to learn about matplotlib. And you typically, what you do is you find an example that you like, right? And you say, well, that looks like a useful example, so let me see how I would run that. And you could copy and paste all that. But matplotlib always has source code links, so you can copy the source code link and then tell this guy to do, let me give you guys the one that has a larger prompt. Load pi, the URL, and then it will go and fetch it and put it in here so that you can actually edit, and when you're done.
Oh, this is multi-line editing too.
Yes, yes, it has proper syntax highlighted multi-line editing, and then you run it, and it fetches it, and the URL that you give it can be a local file path or a remote one as long as you have a connection. And yesterday we checked, we do have a very good connection. And so you can run your examples, you can go back in here and change something, so you can change, I don't know, mu is now 130, we redefine what IQ means, and then we have a different distribution, and then we have display the usual history works, and so now we grab all the figures and we plot them. This is a bug in the Qt SVG renderer. It's not Matplotlib's fault. Qt doesn't implement proper clipping of SVG paths, so it's a bug in Qt. That isn't really, it's more of a limitation than a bug. They said they're not going to fix it. They implemented a simpler spec. Well, they implemented the basic SVG spec, not the extended SVG spec. So these are the kinds of things that it can do. It works in two processes. This is already in trunk. It's already available. It's already, I mean, we haven't released this version, but it is in the master branch. And we're working very, very hard to get O11 out the door as soon as we possibly can.
Can we have this as the Sage command line interface?
Wouldn't this be cool?
Yep. Yes, you will. There will be some changes needed. We've refactored all of IPython internally. It's much more cleanly structured, but a lot of the Sage digs pretty deeply, so there will be some work. It's not going to take. It's not going to be 5 minutes because we've changed a lot of things internally. But absolutely, we've tried to preserve the important stuff. It's just that there will be a little bit of growing pains in the transition.
Are you planning to ship a copy of the 0MQ source code so that when you build IPython, you build that as well, or are you going to make it a dependency? What's your plan there?
0MQ is going to be a dependency.
Okay, that's fine for us. I mean, we can easily add it.
Yeah, 0MQ is already included in EPD and in all the Linux distributions. So it's already made it to EPD and to the Linux distribution.
I've made Sage packages for this. So.
Nthought Python distribution. It's a big bundle of Python libraries, and one of the big appeals of it is that it's a single-click native Windows installer. So it's a very good way to get people on Windows to have a complete installation of native Python tools, and it's free for academic use. So in university environments, it's a very good solution. So that kind of gives you guys a quick idea of what this thing can do. Yes, question?
Do you have one that shows what other people are typing? Like,
not in real time yet, but the whole idea of defining, so it hasn't been implemented yet, but if you turn debugging on and you look at the stream of messages, all the information is there. And in fact, when Brian and I implemented that first prototype, we actually did capture those messages and print them at the command line, so you would see what the other person had typed with a little bracket, just to see that it could be done. Now, the user interface part of that is actually a delicate problem. How do you display information that's coming from multiple people typing? Do you put it in a pane, in a widget? What do you do with it? But the data is all there, and the whole point of that protocol was precisely to ensure that the design had that baked in from day one. So a little bit quickly about parallel computing. As I said, I'm going to try not to run over too long, but this is an important topic. Why should we care about parallel computing? Because that's what computing looks like today. That is a curve of Moore's law. Is the green line, that's transistor count for chips. It does keep going up, doubling exponentially, but the problem is that you don't actually care about how many transistors are on your computer, you care about how fast it runs. And that curve flattened out. We all know that they're selling us multi-core machines, and the reason that curve flattened out is this curve. This line has the power dissipation per unit square area of a CPU as a function of time, with a few important familiar objects plotted on that line, and by 2008, chips had to dissipate roughly at the rate of the surface of a rocket engine, of the nozzle, the surface of the nozzle of a rocket engine. Right? We do not know how to manufacture materials that can sustain that kind of power dissipation. We simply don't know. We don't know how to do that. There is no known material that can do that, so they basically had to stop making them run any harder and tell us that multi-core and parallel computing is the way to go, and that it's great, and that it's still faster because it's easier, and it turns out it's a pain in the ass. And we all know that it's horrible, but we have to do something about it because thermodynamics isn't exactly going to change. In Python, we have serious problems because the infamous global interpreter lock prevents more than one Python. Python has very good thread support. But the threads in Python can't do anything CPU intensive because they can only, there is a lock that prevents more than one Python instruction from running at the same time. So you can spawn a bunch of threads to wait for network data for I/O. You can't do CPU intensive work in them. That touches any Python visible structures. So if anybody's interested in this, David Beasley, who used to be at UChicago, has a phenomenal amount of work done on analyzing the internals of the GIL and doing as much as can be done to improve the situation within the GIL. But if we want parallelism in process There's some things you can do. You can do data parallelism with threaded libraries. You can use a threaded atlas. I don't know what atlas Sage builds, if it builds the multi-threaded one or not. There are tools to do basically parallel NumPy expression. NumExpr is something that takes NumPy expression and effectively compiles them. It's sort of a mini virtual machine specialized for NumPy. Theano is a very interesting project from Toronto CS department that is basically the marriage between a compiler and a symbolic computing system, a computer algebra system. It kind of goes to the question you were asking about the marriage of these things. So Theano basically takes high-level descriptions of functions in terms of high-level primitives and does symbolic transformations on them to emit fast code either for multi-core or for GPUs. Very interesting. You have the GPU stuff. You can handwrite threaded code, awful. If you want to work out of process, Python has had a very good solution, multiprocessing. It's pretty nice. In 3.2, there's something called Python Futures. There's a bunch of other tools, and we'd like to think that with IPython, we have something to offer now as well that is actually fairly interesting. This is all work that we've been doing with Min and Brian over the years. As I mentioned before, we had, and William alluded to it, we've had an implementation using Twisted for parallel computing. But what we did was we took the same diagram that I just explained and the same sockets that I just mentioned for interactive work and pushed them into the idea of parallel computing, where now you can have N engines that do the kind of code execution that I talked about, and these can be many. These engines all connect to an object that looks very complicated, but these are all little 0MQ entities that do all the communication. So it's actually very fast, very efficient, and doesn't bottleneck nearly as badly as Python used to, Twisted. And this controller, plus all of its engines, define the entity that clients can connect to and make requests. So the global architecture is actually fairly similar to the high-level abstractions that we had with Twisted. The performance is very different. This is a log plot. This is not a linear plot. And on that log plot, what you're looking at is task latency. So how many tasks can we, empty tasks, can we send back and forth trying to saturate things out? And with Twisted, we more or less saturate at roughly somewhere between 10 and 50 tasks per second empty. That's the frequency, which means you can't do anything that's high frequency with the old implementation. Your tasks have to be chunky because the latency cost of sending a task is pretty substantial. And worse than that, the cost, your latency, your throughput drops as the number of tasks gets higher. Okay. So, wow. I won't do that again.
One of the Twisted developers is out there.
and so they have museum-level sensors to protect against people getting too close, I guess.
It is important to note that most of these problems are not problems with Twisted, they're problems with our implementation with Twisted.
Good. Disclaimer.
Yes, very, very, very
Twisted
important.
can actually, if you write good Twisted code, and if you could write Twisted code that's relatively similar to the 0MQ code, and it would actually be pretty close.
Yeah, we could say the same about the Sage notebook. Our code looks like that, but probably a Twisted genius can make it look like that.
Our understanding is that Twisted is extremely hard to...
But it's possible.
Yes, it's
Well,
possible.
if we did the same thing of decoupling the schedulers, and we ran those in the same decoupled manner, and the actual main cause of the huge drop is that the way the client is written, that it's always receiving the results at the Python level, and so if you've got results coming in, submitting new work is going to be slowed down by handling the results. And with 0MQ, you can not do that until you ask for them, even though they'll be in local memory. In 0MQ, they won't have hit Python yet, so they can't get in your way.
Nice.
Because they basically get buffered by the 0MQ object that is holding them until you ask for them, and when you ask for them, they're here because they got buffered over here. So when you make a request for an object, the request doesn't go over there. If the message was already sent, it's already sitting there in your C++ side of things, and you just fetch it locally. And throughput is also substantially better, and this is an area where Min did a lot of work on ensuring that no unnecessary copies were made, so that as you're sending, this is sending back and forth echoing arrays of NumPy arrays of increasingly large sizes. And what happens, not only are we also a couple orders of magnitude faster in terms of the number of arrays we can send back and forth, but furthermore, we only start dropping when the size of the arrays gets very, very large, whereas twisted starts dropping significantly earlier, and that's partly because of the amount of copying that twisted does. And with 0MQ, Min worked very hard to ensure that no unnecessary copies were made. We don't have enough control over twisted's internal handling of messaging to make it possible to prevent copies. Twisted will make copies of stuff no matter what you try to do.
Yeah, 0MQ has this clever way where you can tell it not to make copies of data if you're very careful about respecting the assumptions.
You can thank him for that.
Yeah, I looked at that. That looked really useful.
So this thing exposes multiple usage patterns. You can have a direct interface where you can control directly where things get run, but you also have a load balance task interface. You can push and pull data from engines. You can do scatters and gathers in the usual manners. We have some decorators that encapsulate common patterns, and this is already fairly well documented. We try to propagate exception information in a useful manner. And very interestingly, the last point, Min just coded up a demo of actual MPI-style communication. With Twisted, we didn't even think about that. We said, you can instantiate an IPython cluster for the high-level control with MPI support, and you let MPI do the inter-node communication, because the latencies were so high that there wasn't even a point of thinking about node-to-node communication. But Min just took a PDE, a 2D wave, PDE wave example written in MPI from Hans-Peter Langtangen, and we wrote it with node-to-node communicators, either standard nearest neighbor or all-to-all communicators, using only 0MQ. And I mean, he did that just 2 days ago, or a week ago, but the performance numbers are within the ballpark of MPI. And writing good MPI code. What's that?
It's not that fast.
Wow.
And writing good MPI code, we haven't done large-scale testing. We just got some accounts set up yesterday on some of the larger Berkeley clusters to start testing on a larger scale. But writing good MPI code is hard. It's really, really hard, and it's not a very pleasant library to learn. And so if the same abstractions that you learn for the high-level stuff can be pushed all the way into real Perl computing, all of a sudden this opens a number of really interesting doors. So we're kind of excited about this.
How advanced, or like how complicated of a topology can you handle? Do you know?
Probably arbitrary. I mean, you can define the connectivity any way you want.
Yeah, the main disadvantage is that you define, you have to set up the connections.
I see.
So that, but you can set them up however you want. And 0MQ, the way they talk about it, the 0MQ is designed for what they call internet scale. So it should scale to, millions of sockets is how this. And it also, you can use InfiniBand as it natively supports InfiniBand interconnects.
Wow.
So, I mean, this is very new. We have very few, these are the kinds of things, once we understand what the right patterns are, we can bake in support classes that handle at least the more common cases for you in an elegant way. Right now, this is just beginning to happen, but the fact that it's even possible is actually kind of a very exciting possibility. So here's a neat trick. If you have a problem where you can define, for example, you want to define a bunch of things to be done, and you know what the dependencies are, and this is not a party trick. It's a neat trick, but it's not a party trick. We actually have a use case for this. You can define the output of random DAG. It's a directed acyclic graph generated by network X, 32 nodes and 128 edges, fairly sparse. And so you can say, well, at each of the nodes of the graph, my job is to do whatever. In this case, wait for a random amount of time. We're just testing the analysis of the graph topology, right? And so you make a client that's connected to your cluster. You want to hold your results, and then you do a simple topological sort of the graph, and eventually we'll write a little high-level wrapper that takes care of the whole thing. You pass it a graph, and it does this for you. But the point is, it's 2 lines of code. You say, you find what are the dependencies of my particular node. You ask for the predecessors of the node, and then you simply say, I want to apply the specific job for this node but I want it to run after its dependencies have been met. That's all you have to say, is I want that guy to happen only after its dependencies are met, and then you can get your results. And this figure demonstrates that it was done correctly. And this is a very neat visualization that Min did for the examples in the docs. This is already up on the website. It shows that it was done correctly. How? This is network X's DAG representation, so where the line is thicker, think of that as the arrowhead. So time runs to the right in this figure, and where the color indicates where the task was run. So if you imagine I think there's 4 colors in here, so this would be a 4-node cluster. And the point is, if an arrow slants to the left, a dependency was broken because it was run earlier, but you can just visually inspect, it was validated by actually checking, but you can just visually see that all the arrows slant to the right. Now, the vertical axis was used to just put the time of the task, just to spread the graph out a little bit for visual support. But basically, the point is you have a big complicated thing where you have a data flow, you pass the DAG to the thing, and it does the right thing out of the box. And this, as I said, this is not a party trick. We have some collaborators at MIT who have written a neuroimaging pipeline system where you describe a flow that can call multiple things for large-scale data analysis, and what it produces is a network X DAG. So that thing produces a network X DAG. When we started working on that, I mean, that's not my work, but we collaborated with him closely. A decision was made early on to represent the data flow as a network X object. Well, now we can just take it. And they're actually already using IPython to parallelize it, but the old IPython, the twisted code. So they do a lot of manual handling of this. Now it's completely done at a high level. Some other tools, you're familiar with Matplotlib. I'm going to stop with IPython. You're familiar with Matplotlib. It does 2D, it does 3D plotting. It's beautiful. You've all seen Matplotlib plots. One important point to keep in mind is that Matplotlib, in addition to great quality images that Sage uses, and having a familiar high-level API, it is a library that is very rich in the kinds of ways in which it can be used. You can plot with all the GUI toolkits, as I said. The GUI windows have interactive support for navigation and zooming and panning. They have event handling that is independent of the GUI toolkit. You get proper LaTeX support without the LaTeX dependency because Michael Drudbaum here actually tackled Knuth's digital typography book and implemented the text layout algorithms in Python. Since LaTeX is not a library, you can only call it as a sub-process. It's kind of a pain in the neck. So Michael just bit the bullet and implemented it in Python. So Matplotlib has an implementation of the text layout algorithms, and that's why you can do math in Matplotlib. And you can embed it in GUI apps. Sage has taken the, in my opinion, wide decision of building technologies based on a web toolkit, but there are many people who have valid needs for local GUI applications in WX or in TK or in Qt, and because Matplotlib widgets can be embedded in all of these, it's a really, really powerful library because the same machinery, the same plots that you're doing interactively when you're exploring, you can obtain the exact same results in some GUI application that's controlling some hardware instrument, for example. And that is very, very widely used in the scientific computing world. Mayavi is the 3D fancy 3D visualization tool that many of us use, which is a beautiful example of how to properly use Python to do work, because it's a system that lets VTK, which is a large, complex C++ library that works with OpenGL to do all of the 3D rendering, to do the heavy lifting of 3D rendering. That is deferred to the C++ layer, but it binds VTK with very nice, easy-to-use high-level bindings that know about NumPy arrays, so that you can basically have an easy interface to VTK. For those of you who here has written native VTK code? Okay, nobody. Good for you. Good for you. It's awful. You read the VTK examples, and just to get a very simple surface plot, the kind of thing where you think, I want to plot a surface that z equals some function of x and y, the example is that big. And you have to understand the pipeline and the actors and the filters and the transforms. It's written in that language of really awful, low-level things. In Mayavi, you say mlab surf, x, y, z, and you get it. And z is either an array or a call of an array, and then you evaluate it, and that's it. So it provides the kind of high-level interface to VTK that you would want to use. Python allows you to, the menus are defined in Python, so you can extend it. This is an example, it embeds IPython so that you can run a script down here, manipulate the data structures that you have in here, and they update live here, so you have both the GUI for the menus and the filters and whatnot, but you retain interactive typing control over what's being visualized. You can define in Python custom plugins, so that in the menu, this was work that we did with some grad students at CU Boulder, that would load a very funky format for fluid dynamics visualizations that was generated by supercomputers at NCAR. And so we added one menu entry to Mayavi to understand that data format. And after that, it would load the data into Mayavi, and then we had the rest of Mayavi for all the modules and filters and all of the rest. So all we had to do is write one little snippet that would provide that menu entry. And then we would live inside of, basically Mayavi would open with our plugin to control what slices of the data set to load and whatnot. And then we had the rest. You can even drag, and here, dragged means that I grabbed something from the UI and dropped it with the mouse. and then I can access that array. So you can actually grab elements from the GUI, drop them in the command line, and operate on them, which is very neat. Another tool that is increasingly important for us is SymPy. Lightweight. I know that Sage has enormous amounts of work done via Maxima, but SymPy doesn't have all the power of Maxima, but it's a very neat, lightweight, pure Python symbolic library that is growing and can do a number of really useful things. For example, with some fellows from Stanford, we're working on a SymPy-based way of describing statistical models to basically provide something like what the R formula syntax is, for those of you familiar with R, but with a proper symbolic algebraic machinery behind it, so that you can do sensible operations on your statistical models before you evaluate them on a data set and try to do the estimation, which at that point is basically numerical operation. So this is really a useful tool. Things are growing very fast. Discipline-specific workshops are beginning to pop up in various places in the world. The SciPy conference is what started in 2001 as a very small workshop at Caltech. This year it's in Austin in July for those of you who can make it. EuroSciPy this year is in Paris, started in 2008. There's been a SciPy India, so I'll be speaking at EuroSciPy and had a chance to go to India to talk last December. The Indian government is putting a lot of effort into funding open source development for their scientific and engineering and education without resorting to proprietary technologies. There was a Japan SciPy being planned. I have no idea with the current mess in Japan whether that's still in the works or not. Some people were planning on it. At the SciAm conferences, I want to mention that, so in 2008, we organized with a U-Washington Professor Randy Levesque at their annual meeting. We organized a meeting about Python for scientific computing, and there was a fair amount of sort of evangelism. Yes, you can use Python. This is SciAm, the Society for Industrial and Applied Mathematics, or sort of the private hunting grounds of MATLAB. It's a heavy MATLAB-dominated world. And so we were sort of saying, you can do this with these tools, and no, we're not crazy. Then at their Computational Science and Engineering meeting in Miami, we also organized with Hans-Peter Langtang and another one that were successful and very well attended. Well, 2 weeks ago was the 2011 edition of their CSC meeting. It's a biannual meeting. And Hans-Peter and Randy and I did it again. We had no evangelism this time. There were just talks focused on the tools, which was great. But what we saw was not only did we have our mini symposium, there were 3 other sessions devoted to Python by other people. 2 about PDEs, 1 about optimization, made by people from completely different projects. And in addition, so there were a total of 5 sessions. Our session, the first part of it, was standing room only, which I've never seen that at a SciAm conference. The Perl sessions at SciAm are typically fairly sparse, to put it generously. And we had literally standing room only, so there's a huge amount of interest in the applied community about these tools. And in addition to the 5 independently organized Python sessions, there were a ton of talks that had Python in the title. I'm putting together a collection of all the slides, and we'll post them online later, because I gathered the slides from all the Python-related talks in one place. So it was a very interesting data point to see the rise. We've done this 3 times, and we could sort of see how the curve of interest is going. Sage Days at Supercomputing 09, apparently there were some very well-attended Python sessions. I didn't go. In education, as I said, India is putting a lot of money into it. The NSF had some projects. Obviously, the NSF has been funding Sage in various forms at some point. MIT switched their basic CS program to Python a couple of years ago. At UC Berkeley, a colleague, Josh Bloom from the astronomy department, last semester got some funding to have a boot camp, a 3-day boot camp at the beginning of the semester for all grad students. Paul and I lectured at that boot camp. And then during the semester, a full semester graduate course of sort of scientific computing for grad students in any field who wanted. It was very intensive. They were doing hard problems, and I think it was very useful and very well attended. The CISC journal, which is a joint publication between the IEEE and the American Institute of Physics, had a special issue in 2007, and another one that just came out, where Robert Bradshaw has an article on Python, Brian Granger and John Hunter and I wrote another one, there's another one on NumPy, there's another one on Mojave, so there's a couple of articles on sort of everything that I've talked about. It was focused on the numerical side of things, and that's a publication that has a fair amount of circulation, and it's a kind of an easy to read thing. In industry, the national labs at this point are all sort of on board. The PDE sessions and the optimization sessions that I mentioned were organized. The PDE stuff was mostly Argonne and Sandia. The optimization stuff was mostly Sandia people. So the national, and NIST as well. The national labs are definitely using it extensively. Industry uses it a lot. So to wrap up, because I've already well overstayed my welcome, I think that in this audience I don't need to sort of belabor the point that there's two sides to this. On the technical side, we have a very, very good tool for the kinds of problems that we're trying to do in today's scientific computing contexts, and Sage is an excellent example of using this to its full extent. But also social considerations, that these are tools that we are developing because we need them, because we want them. I'm personally convinced that black boxes don't belong in research, at least in the critical path of research results. I don't care if you use a closed source tool to write your papers, whether you use Microsoft Word or LaTeX, that's up to you, what kind of thing you want to inflict upon yourself. But research results should not be hidden behind a black box that we're not allowed to verify and validate, and at least inspect and critique and understand. And I suspect we all agree on that point. But also, and the last point is a point that is close to home, hits close to home for me. I come from Colombia, a country with very limited resources, and that's the same argument that India made. With the little money we have, should we spend that money in paying an annual rent to commercial software houses, or should we invest that money in developing tools where our students learn as part of the process of developing them, they become active participants of the scientific process, and they can further share what they're doing after the fact. And I think they made a very wise decision in that regard, but there's still a lot to do, both on the Sage side of things and on the sort of numerical scientific side of things. And so I hope that those of you who are new to this at this workshop will go back to your home institutions and continue contributing on whatever front it is that you end up contributing. So thanks a lot, and sorry for the very long talk. If there are any questions, if not, we can break out for other work, and I'm here until tomorrow night, so I'm more than happy over lunch, over coffee, at any point to chat with anyone, because I know it's been a long talk.
Question? Okay, so let's have the status reports in about 10 minutes, and that's it.